Hi everybody. Let's continue our volume by cross sections part 2. In our last lesson we did volumes, calculating it using our cross section being squares, and we talked about the way we come up with these volumes are pretty much we're just multiplying a little bit of the area by a little bit of dx, and these slices end up adding together using our integration to form a full volume. So for our squares, let's just draw this out very quickly. For a square here, if I give you some type of curve, we can call this f of x. And if I start building out squares, like that, like so, you end up with a 3D model here. And we can find out what the volume of this model is by pretty much adding up the little squares sizes. We're just going to add the squares together and infinitely many times. And for us, since we're just adding, these slices of squares are infinitely small, but if you add enough like layers together, you end up with something really thick. Let's start our volume. So we said we're going to add up, so our volume equation is the sum integral from a to b, our starting to ending point, and we're just adding up squares, which is just this length from here to here, and we'll call it s for the side. And in this case, the side would be f of x. So we're just going to call that s squared because it's just a regular area of a square multiplied by a little bit of dx. And by us multiplying a little bit of area with a little bit of width, we end up with our volume. And we add up all these volumes together. Okay. Our semicircle, very similar, except a couple of tricks out of our semicircle is that we are forming half circles. So if I draw my line here and draw a little half circle, our area formula for this half circle is pi r squared, and we divide that by 2. Half pi r squared because it's half a circle. But there's a gimmick here. The radius here is not the full f of x function, it's not the full y value. It really is only half of it. So if we call the whole side s, that means the radius is 2r, you could say, because there's 2 radiuses. So the radius is equal to s over 2. And if we want to plug that into this equation, it's going to be 1 over 2 pi s over 2 squared. And when we square s over 2, that gives us s squared over 4. So 1 over 2 pi s squared over 4. Combine those to be 1 over 8. Let's say pi over 8 s squared. Now this is our area equation for each of these slices of semicircles. So for our volume equation, again, we're just multiplying the area times a little bit of width. Since a pi over 8 is a constant, we're going to throw that outside our integration. A to b of s squared dx. For isosceles rectangle, we had 2 types. One was it's sitting on its leg, so the right angle coming up. And the other one was it's sitting on its hypotenuse. Okay, sitting on its hypotenuse. So we had 2 different versions here, depending on which way the problem throws you. If it says sitting on your leg, let's look at this picture. And this would, so this would be our s side, because that's the full length. That'd be our s side. But we said this was just half a square. So this equation here for a leg on base would be the integral from a to b of s squared dx. And since it's only half the square, we throw a 1/2 in front. Well, the hypotenuse one, we said this was a little more tricky. If I'm drawing my hypotenuse on, let's draw something kind of similar. A curve. And hypotenuse look kind of like that. its its right angle sticking up in the air. Now, to draw this triangle down, let's say this is my S. We said we would break this up into 4 triangles instead, because this is a 45, 45, 90 triangle. So this would be, the area would be 1 over 4 s squared. And that's reflected in our volume equation because it's just 1 over 4 integral from a to b of s squared dx. Now today we're going to go over just 2 more shapes here. And one is the equilateral triangle. So we're going to build our model. This is my function. And we're going to build our model looking like this, where all the sides are the same. This is S, 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 and each of these angles are 60 degrees. Okay, 60 degrees for all 3 of them. Now let's look at a 2D version of this. If I just draw a triangle here, and call this S, S, S for the sides. In this case, the side is also the length of the function. How would we find the area equation for this triangle? Well, a couple of things. A conventional way of just is cutting this in half. And since we had a 60-degree angle, we have a 60-degree angle here. That now becomes, cutting half becomes a 30-degree angle. And this becomes a special triangle for us. 1/2 S for this new base on the right. And this special triangle here is a 30, 60, 90 triangle. And if you remember, there's a trick to this. The trick is that the hypotenuse is double. As you can see, if we 1/2 S times 2, 1/2 S times 2, that does give us our side here on the right. And we, for the height, was a square root of 3. And 1/2 S here, because that was the base. So our equation here for the area of a triangle, and this is 1/2 base times height. Let's figure out what the base is. The full base here is S, so 1/2 S. What is the height of this triangle? The height of the triangle is square root of 3 over 2S. Again, how do we get that? We made this into a 30, 60, 90 triangle. 1/2 S for the base. That's S, 60, and 30. And to multiply this to the height, the long side, is we multiply by square root of 3. And that's our height here. And the base is not 1/2, but since there's 2 of them, there's 2 1/2s. That's why it's a full S. So let's write this in a nicer way. We have 1/2, so 1 over 4, square root of 3 on top, and S squared. So this would actually be our area equation for any equilateral triangle if you know what the base is. So our volume equation for this, since we're adding just up the area from A to B, we're adding the area times a little bit of width. So our volume is integral from A to B, square root of 3 over 4 S squared. Now this will always be the case for equilateral triangles. With a little bit of width, that's called a little bit of dx. I'm going to kick out the square root of 3 over 4, A to B, S squared dx. Now, if you look at this volume equation, and this is specifically for equilateral, equilateral triangles, they all follow this kind of S squared model. For all our examples up here, we had an S squared here, S squared, S squared, whoop, near semicircle, yeah, sorry, that was S squared over here. Our isosceles with the base, leg on base, and this is the hypotenuse on base. They all follow this S squared model. Only thing changes is the constant in front. So let's look at our last shape. The last shape is a rectangle here. And the rectangle really can change depending on the situation. Sometimes they'll tell you the rectangle is twice the length of the base. The height is twice the length of the base. So let's draw you an example. So a rectangle, if this is my base, sometimes they'll say this is twice as large as my base. Sometimes they'll tell you it's 3 times as large as my base. Sometimes they'll tell you it's 4 times as large as my base. Now in all these situations, how would you find the area? The area for each of these would just be the base times the height. In this case, it would be the base, s, times 2s is 2s squared. In the next case, where it's 3 times, it'll be area is s times 3s, which is 3s squared. When in 4 times, area is s times 4s, which is 4s squared. What you notice about them all, they all have that s squared model like we did before in all our other cross-section problems. So our gimmick here is to just figure out what's the relationship between s and the area. So to talk about volume again, volume is just, again, we're adding up the area times a little bit of width. So that's going to be from A to B. And it's going to be, our area is 2s squared. Multiply that by a little bit of dx. We can rewrite this with a constant on the outside. Our next problem, just the same way. We're multiplying the area times a little bit of width to give it a volume. And the area equation is 3s squared dx. Since this is a constant, 3 is a constant, we're going to kick the 3 out. The volume is 3 integral from A to B of s squared dx. And what if the rectangle, the side was 4 times as large? You can probably predict that it would just be volume is 4 integral from A to B of s squared. Okay, so let's just do one example. The example is my boundary for the function f of x is, let's say it's going to be the square root of x, very common problem. And our boundary is going to be from x is between 0 and, let's do 4, 0 and 4. Okay, and we're building up from the x-axis. So we can draw a basic graph of this. Here's our 4. Square root of 4 is 2. 2. And we have a square root graph here. And we're going to build, let's go ahead and build rectangles. Rectangles, where the height is, let's say, 3 times the base. Height is 3 times the base. So whatever base this is, the rectangle is going to pop up 3 times as tall. So 3s. So our volume equation, well, let's first find the area equation, because we need to find the area. The area of this cutout here, this cross-section, is the base is s, and the height is 3s. So the area would be 3s squared. For us, the s equation is just our function equation, which is just the square root of x. So instead of writing s squared, we're going to write the area is 3 square root of x squared. Right? Because if I wrote s is just really square root of x, and s is really just square root of x, it would still be multiplying square root of x and square root of x. And this still leads us to just saying it's just 3x. And that's our area. Our volume equation is from A to B, from 0 to 4, of my area times a little bit of width. My area we said was 3x. My little bit of width was dx. That's it. That's how we set up.